Good morning, good afternoon, good evening, whatever the case may be. Let's rage on the vector product of two vectors, shall we? We don't need no Juicy J or KDP. We have got mathematics. So, vector product of two vectors, part one. This will become, these two things in particular will become quite meaningful to you, I believe, in part two. We shall see how far we get. So, here we go. We've already talked about the scalar product, and the scalar product of two vectors is a scalar, it's a number. The other product between two vectors that we have is the vector product or vector cross product. And I will almost always refer to this, as many others do, most others do, as the cross product, just like we refer to the scalar product as the dot product. Okay? So, what is the cross product? The vector product arises, or the cross product, when we attempt to find a vector which is perpendicular to two other known vectors. Well, what does that look like? Well, let's take a look-see. Let's say we got two vectors hanging out. I don't know, two random vectors like here and maybe there. Okay? And any two vectors, just like any two lines or rays or whatever, that aren't in the same direction or aren't the same line or aren't the same ray, they can form a plane no matter where they are. So I'm just going to move this vector over. And if you can imagine, I don't know, maybe like on a football field or something, I'll put some stripes here. You can see how these are in the same plane. And I could even maybe draw a little rectangle around it, I suppose, just to convince you that they're in the same plane, like on a piece of paper now. You could see how I could take this piece of paper maybe a little bit tilted, and there we go. Isn't that nice? Okay. So then I could, if I took the cross product of those two vectors, the result would be a vector perpendicular to those vectors. And maybe an easier way to think of it is perpendicular to the plane formed by those two vectors, or not necessarily formed, but the plane in which those two vectors reside. So this would just be coming at a right angle to the plane and to these vectors. I suppose I could have, oops, let me draw that vector again. I could have drawn the right angle symbol, like to this vector here. Oops, that's horrible. Let's undo that. I want to do this right like that, and then maybe right like that. I think you get the idea. So when we do find the cross product, we are finding a vector perpendicular to any two vectors that aren't the same vector. Okay? And again, a cross product results in a vector, while a dot product results in a scalar. Okay? So we have to define what the cross product is. And this is a nice proof that, is in the textbook. I'm just going to kind of zoom through it. If I have a vector with these components x, y, z, and it's perpendicular to these two vectors, any two random vectors, a and b. So this is going to end up being my cross product because it is perpendicular to two other vectors. I know that a1x plus a2y plus a3z equals 0 because x is perpendicular to a, and the same with b. X dot b is equal to 0. Okay, and if I subtract these guys from both sides, then I get equation 1 and equation 2. Okay, and we're going to solve these equations to get expressions for x and y in terms of z with some manipulation. I get to here, a1b2 minus a2b1y equals a3b1 minus a1b3z. And that means that y, and if these are equal, y must be equal to this, which is what is stated here, and z must be equal to this for any non-zero t. So that means any multiple of this will work as well because they're going to be equal. Then using some substitution, we end up with solving for x here, and we get x, the x value, because we already have a value for y and a value for z. Yes, this x, this y, and this z, not the vector x. So this y is this y right here, and this z is this z right here. And then with some algebra that you can look at later if you want to, I get a value for x times some scalar t. And so the simplest vector, perpendicular to both vector A and vector B, is given when t is equal to 1. So in this case, we find that the vector x is equal to a2b3 minus a3b2, which comes from here when t is 1. The y component is a3b1 minus a1 times b3, which comes from here, t equal to 1. And then the z component comes from here with t equal to 1. And our a's and b's, remember, are the cross product of any two vectors a and b, which we started with up here. And this is our cross product. Okay? So that, I just copied this from the last page. And in your text, we get a nice little statement here about the vector cross products. A being equal to A1, A2, A3, B, B1, B2, B3, A cross B is what we have right here. So that is how we define the cross product. On your formula sheet, and what we're going to use in all these examples, we have this. They use V and W. Same exact thing except for A and B, we use V and W. Okay? And what I want you to notice here is that for our x component, yes, V2, W3, we just, it works out, this is how I remember it. We don't use our x's here, and we start with V2 times W3, and then we subtract the opposite, V3 times W2. Then for our y component, we don't use the y components. We start with V3, W1, and then we subtract V1, W3. And then for the z component, we don't use the z's here in our original vectors, V1, W2 minus, and then we swap them. Okay, this will come later. Okay, that's a lot of intro. Let's do a couple of examples. We have some algebraic properties. These are for vectors A, B, C, and D, and we're going to go, they're just kind of here for us to look at, and through our homework, we will verify and prove them. We already know that A cross B is perpendicular to both vectors A and B. A cross A is equal to 0 for all A. For any two vectors A and B, A cross B is equal to negative B cross A. This means that A cross B and B cross A, they have the same length, but they're in opposite directions. So if they're in the same direction, we would negate them. The scalar triple product, this is called this, A dot B cross C. And then this is the distributive property. This is the distributive property again that you might know as the FOIL method. So let's do an example. Let's find a cross product. Find A cross B. Okay, so A cross B is equal to, okay, so let's get a nice big vector symbol here. Okay, so I'm not going to use these, right? And I'm going to start with the second component times the third component. So 3 times 4, and this is kind of what, this is why they call it a cross product. If you think about it, I'm crossing here, minus negative 1 times 2. Negative 1 times 2. So you see what I did there? this times that, okay? And so for our z component, we go here, okay? I'm sorry, why did I say z? My y component, I'm not going to use these. Well, what am I left with? I'm left with 2, -1, and -1, 4. So this will equal -1 times -1, the V3, right? So -1 times -1 minus 2 times 4. And finally, we have our z component. So I'm not going to use my z's, and I'm going to start with v1. So that would be 2 times 2. Oops. 2 times 2 minus 3 times -1. So you'll get used to this. You just have to be very careful to start. So this turns into 3 times 4 minus -1 times 2 is equal to 14. -1 times -1 minus 2 times 4 is equal to -7. And 2 times 2 minus 3 times -1 is equal to +7. Okay? So that is our cross product, our first cross product. So let's take a look here. Just some strategies here. So for this first one, I eliminate my x's. I just forget they're there, and I start this way. I go 3 times 4, -1 times 2. Okay? And I do the same thing. I'm going to skip the y component. I do the same thing for my z component. I forget the z's, and I do 2 times 2, right, minus 3 times -1, just making a pattern here, okay? And y is the oddball. I cross out my y's, but instead of starting here, I start down here. -1 times -1 minus 2 times 4, as you see right here. Okay, so that's one way to remember the pattern. Okay, I'm going to stop it there. That's our only example. We had a lot of mechanics to go through. Hope you enjoyed it. I wonder how Katie's doing. Let's see how she's doing as we fade out. Yeah, where's Jazzy, Juicy J, Jazzy Jeff, whatever his name is. I hope you enjoyed it, whatever his name is. I am old. Cause I'm coming at you like a dog. What are you ready for? Ready for? Perfect storm, perfect storm.